Hey everybody, Professor Davis again from ChemSurvival.com and the YouTube channel ChemSurvival. And today I want to show you how we use Newman projections to analyze and depict the rotameric states of simple hydrocarbons. Simple hydrocarbons like this ethane molecule. And we've got lots of ways to draw this that we've already looked at for the most part. Those ways include the skeletal structures. We've got condensed formula. We've also got Kekulé and Lewis structures. And we even have the perspective method of drawing. Now, while the perspective method of drawing begins to show us a little bit about the true three-dimensional orientation of the atoms in these molecules, it still doesn't give us very exact information about the relative locations and bond angles. So in order to fix this problem, we've got to come up with a new way of drawing molecules, which gives us really specific, very rigorous measurements of these so-called dihedral angles between the bonds on adjacent carbons. And this is what Newman projections are for. So let's begin by drawing a Newman projection of this ethane molecule. And in order to do it, I'm going to have to draw the molecule in a new angle, in a new perspective that we haven't really looked at before. Right? So we know that perspective is always drawn when we look at a molecule from the side of the interior carbon-carbon bond. But what if instead I were to sight along the carbon-carbon bond by looking down one carbon atom so the other's in the back? In other words, what if I were to look at the molecule from this perspective? In this perspective, it's much easier for me to see the exact angles between and among the hydrogens on adjacent carbons. And we can draw this in a shorthand version called the Newman projection. The real utility of the Newman projection is that it shows us the atoms in the front, indicated by lines for their bonds that go all the way to the center, and atoms in the back by their bonds being clipped off at the perimeter of the circle. And by looking at this, I can get an exact measurement of the dihedral angle. That is to say, as that carbon-carbon bond rotates, because it is after all a sigma bond with free rotation, I can draw this molecule in any particular rotameric state that I like and show it very specifically using this Newman projection. Let's take, for example, this molecule if I were to rotate it in, let's say, this perspective. So now my hydrogens aren't 60 degrees apart from one another. They're basically almost overlapped. So in order to show this with my Newman projection, I simply draw my hydrogens in back with the same type of perspective. So as you can see, I can now not only draw the molecule showing all the bond connectivities, but I can also show spatial relationships much easier. Okay, so let's get down to business now. When you turn in your book to the Newman Projections page or chapter, you're almost certain to see a diagram which looks like this. This diagram relates the relative energy, or free energy, of a rotameric state as a function of the relative degree of rotation along the carbon-carbon bond. Now, what's trying to be shown here is the following. Let's take a look at my ethane molecule again. Right now, as I've drawn it, the hydrogen atoms on the back are as far away as they can possibly be from those hydrogen atoms on the front. This is because the bond dihedrals are 60 degrees, and we call this a staggered conformation. Staggered conformations are the lowest energy conformers possible because those substituents have as much space as possible available, so there's no steric clashing. But what if I rotate this carbon-carbon bond by 60 degrees? Notice what's happened now. My substituents are all directly in front of and behind one another. So we call this the eclipsed conformation because those substituents in the front are eclipsing those in the back. And in this conformation, they're as close together as possible and therefore have the greatest amount of steric repulsion. What this means is that having rotated this carbon-carbon bond by 60 degrees creates a higher energy rotameric state. In the case of ethane, this difference is about 12.5 kilojoules per mole. If I continue to rotate my carbon-carbon bond and go another 60 degrees, I now have another staggered conformation, lowest in energy. Another 60, I reach a new eclipsed conformation. Yet another 60 degrees, takes me to another staggered conformation, and so on, until eventually I've completed an entire 360-degree bond rotation. So my final rotation takes me back to the very beginning, and I can place this at the other end of my diagram. So what you're looking at when you look at one of these diagrams is the relative energy of the different rotameric states. And if we want to predict the behavior of an ethane molecule, we're going to look for the lowest energy conformational or rotational state, because there will be more ethane molecules in a sample which look like those low energy species at any given time. And naturally, to predict the reactivity of a compound, we want to use a model that best approximates most of the population within that sample. So this is what you're looking at when you look at these energy diagrams and Newman projections. That's all for now, guys. I'll see you next time.